This next theorem does not show up in our textbook. It shows up in some books but not others, but it's a nice little handy theorem. It says if the sum of the coefficients is 0, then x equals 1 is a zero of a polynomial, and therefore x minus 1 is a factor. And if, after changing the signs of the coefficients of the odd degree terms, the sum of the new coefficients is 0, then x equals negative 1 is a 0. Now that looks a little bit scary, but let's try this here on our first function. I'm going to test whether 1 is a 0 of the function. All I'm going to do is add together the coefficients that I see here and see if they equal 0. This clearly is 2 negatives, so the answer is no. That one's not 0. Let's test to determine if negative 1 is a 0. We are going to change the sign of these coefficients on the odd degreed terms. The first term is an x to the fourth term, so we're going to keep it as a 2. But the x cubed term has a coefficient of 9, which is going to change to a negative 9. X squared, keep the negative 5. Odd degree term here, so negative 57 is going to change to positive 57. And negative 45 comes down. And now when you add these together, you do get 0, and that tells you that negative 1 is a 0 of our polynomial. So now we begin the synthetic division process, and I'm going to put negative 1 out there in my little box, and we're going to have 2, 9, negative 5, negative 57, and negative 45 as coefficients of our dividend, and bring down the 2. Here we go. Negative 1 times that 2 is negative 2. Add down, get 7. Negative 1 times that 7 is negative 7. Add down and get negative 12. Negative 1 times negative 12 is positive 12. Add together, get negative 45. And you can see that we're going to have 0 at the end here. I can now rewrite my function n of x as x plus 1. Notice I'm changing the sign from the divisor to the factor, and I'm going to have a remaining polynomial here beginning with x cubed, so 2x cubed plus 7x squared minus 12x minus 45. Okay, we've broken the fourth degree polynomial down to a linear factor and a cubic polynomial. Now we need to try factoring yet again. Okay, how do we do that? Well, we can, since 1 wasn't a factor up above, 1 won't be a factor down here. We can try the technique here by changing the signs to see if negative 1 works a second time, but it won't. And so now we use this new polynomial, and we try looking at the leading term and the trailing constant to help with the rational zero theorem to come up with some leads. We're going to have 1, 3, 5, 9, 15, and 45 as factors of 45 there, and this will help us to generate terms to try when we try to break down this second polynomial. So here we go. 2, 7, negative 12, and negative 45 go up on top, and we know 1 won't work, so let's try 3 over 1. So here we go. 3. Bring down the 2. 3 times 2 is 6, plus that 7 is 13. 3 times 13 is 39 minus 12, which is 27. 3 times 27 is 81 minus 45, that's 36. No way. Let's try negative 3. Bring down our 2. Negative 3 times 2 is negative 6, plus that 7 is 1. Negative 3 times 1 is negative 3, plus negative 12 makes negative 15. Negative 3 times negative 15 is 45 minus 45 is 0. Ding, 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 we found a winner. That tells us n of x, coming down from up above here, is still going to have a factor of x plus 1, but we just found out that x plus 3 is another factor because of the minus 3 that we just got there. And now the remaining polynomial is going to begin with an x squared term, and we will have 2x squared plus x minus 15. But this is a second degree term, and we know how to factor those, so we'll leave our x plus 1 and our x plus 3 out front. We will have 2x in one parenthesis and x in the other, and it turns out that it's 2x minus 5 times x plus 3. And so our zeros of this function are -1, -3, and 5/2, and it turns out that that -3 shows up twice, so it has a multiplicity of 2.